So look at practice question set number 15. Since XY represents a section of a current carrying wire, conventional current, you guys remember what that is? Talked about that a little bit yesterday. Conventional current is what? What is it? It's full of positive charge. And we don't very often see that in physics 30. In fact, this could be, I'm not saying for sure that this will be the case at all, but this could be the only time you ever see it. It's very seldom that we talk about conventional current in physics 30. But if we do, you know that it means the flow of positive charge. So if you're going to use a hand rule, context of magnetism, you're going to use a hand rule, make sure you use a right hand rule, the right hand wire grasp rule, or the right hand coil rule, whatever the case may be. So this is conventional current flowing in the direction of the arrow. The magnetic field at any point around the wire is found using this formula. Now, we've never seen that formula before. That's okay. Sometimes that happens to us on a diploma exam. They give us a formula we've never seen before. If that does happen, they'll always explain it. They'll always tell us what the variables mean like they do here. So we don't need to stress about that. Tell us the magnetic field is equal to this constant. It's called mu. R is the distance from the wire. I is the current through the wire, XY. We want to find the direction of the magnetic field produced by the current at point P. You want to find the direction of a magnetic field produced by moving charges. This is where you use the wire grasp rule. So we're going to say right hand, thumb, in the direction of the moving charge. I'm going to use this meter stick as my wire here. My thumb points in the direction of the moving charge. So thumb to the right. My fingers have to go above the wire, like you see here. Which way are they pointing when they're above the wire? Right? Away from the page, or out of the page, yeah. So the answer is going to be A. Note that little dot there, that's not meaning out of the page. Like, don't say out of the page because, oh, it's a dot. Right? That little dot is just indicating a point, right? They're not trying to tell you a direction there, otherwise they wouldn't be asking the question. They're just saying, at that spot, at that one spot, which way is the magnetic field? And it is out of the page. 2, if the current in conductor XY is doubled and the other variables remain constant, then the magnetic field strength at point P will do what? Well, if we say that this is my original magnetic field, then my new magnetic field would be equal to u sub 0. I doubled the current, right? So it becomes 2I over 2 times pi times r. Now there's a temptation here to say, well, 2 over 2 is 1, right? So they cancel. Don't do that. We don't want to do that because we want to keep this equation looking as much as possible like my original magnetic field. So I'm going to pull the 2 on the top out front. I get 2 times mu times I over 2 pi r. That's mu times I over 2 pi r is the original magnetic field. So we're going to say that this is 2 times the original magnetic field, which means the answer to this question is going to be increase to double its present value. How many people got that? Now, just as an aside here, you don't need to know this, but just as a little aside here, remember yesterday we had a question on I think it was a practice question set that we did yesterday, where you had to, remember that Venn diagram question where you had to compare the similarities and differences between gravitational, electric, and magnetic fields? And one of the questions talked about the relationship between the field and R, the relationship between the field and distance. Remember that? And we had to recognize that the relationships that were given were not the relationships for magnetic field and R, even though we didn't know what the relationship was. We used some logic there, right? We said, well, we haven't learned the relationship. This can't be the answer then. You still really haven't learned the relationship because you don't have to be taught. You don't have to know the relationship. But this is the equation that describes it. So we would say the magnetic field is not related to 1 over r squared or to r squared like the two options yesterday, but rather it would be 1 over r, as you can see in this equation here. Not that you really need to know that, but I guess just a justification that the answer that we said yesterday was the correct answer. All right, next question. Number 3. The north pole of the solenoid shown below is at position what? Hey, which side of the battery is the negative side? Left side or right side? The right side. So that's the positive side on the left side. Right side is negative. That means the electrons are going to flow this way, down in the front, up in the back. If you don't have your coil still, that's okay. If you forget to bring your little coil to your unit test, which, by the way, I'll allow you to bring it into your unit test, not your diploma exam, but your unit test. You can make one yourself in your diploma exam, right? Make it right in the middle of your diploma exam. Just ask for a piece of scrap paper and make one. Takes about 5 seconds to make one, right? Just made it. Here's my coil. I'm looking at the word front. Pretend the word front is printed on this. You're looking at the word front. My fingers have to go down in the front, or I could do it up in the back. My thumb is going to automatically point to the left. Good. So the magnetic field inside here, it points to the left, which means this is what? South or north? Is it? Nope, not south. Where the magnetic field inside points from south to north, outside it points from north to south. Does that make sense? Now notice I used my left hand for that because I was using electron current. Had I chosen to have the current going this way, that would be conventional current. And I would use my right hand, and I'd still get the same answer. Okay? I wouldn't do that. I like to use the electron current. I'll always do that, unless they specify conventional current. But in the end, you're going to get the same answer either way. Question?
Is the negative side of the coil always going to be the right side? Or is that whichever?
No, it's not always going to be the right side. That's a good question, though. If you have a battery that looks like this, the right side would be the negative. If you have a battery that looks like this, the right side would be the positive. The short end is always the negative, and the long end is always the positive. Does that make sense? Here's the way I remember that, personally. I don't know if it's a good way or what, but it helps me remember which end is negative and which end is positive. I think, okay, the longer vertical line, we have two vertical lines here. The longer vertical line is the sign that has a vertical line in it. Right? Negative doesn't have a vertical line in it. The positive is the one with the vertical line in the symbol. It's the one with the longer vertical line in the actual symbol for a battery. Okay, does that make sense? So I don't know if that helps, but it helps me. And you guys are probably just better at remembering it, and you don't have to have a way of remembering it like I do. So we're looking for the North Pole, so the answer would be A for that. 4, if a current-carrying wire runs directly over a magnetic compass, the needle of the compass will point which way? If this is my wire, the magnetic field either goes this way or this way, correct? It's either going to go clockwise or it's going to go counterclockwise, correct? Well, the compass should point in the direction of the magnetic field. So if the magnetic field is either counterclockwise or it's clockwise, the magnetic field at all points around this wire is perpendicular to that wire. So isn't that the way the compass should point? Perpendicular to that wire. So the answer for this one would be A, perpendicular to the wire. Listen carefully to something I'm about to say here. For the rest of this unit, and for next unit as well, our EMR, or electromagnetic radiation unit. If you're confused about a direction, odds are the answer is perpendicular. Okay, we're going to see perpendicular so many times throughout the rest of this unit and our next unit. If you're not sure, you should guess perpendicular, because 90% of the time, perpendicular is going to be right in terms of a direction. Not for electricity, but when you're dealing with magnetism, the answer is almost always perpendicular. And when we're dealing with electromagnetic radiation, the answer is almost always perpendicular. And it is here. 5, an automobile's battery delivers a steady DC current. That's a direct current. It means the electrons are flowing in one direction, and they stay flowing in that direction. It's like a battery. Right? Battery produces DC current. Versus AC current that's used in our houses, that's alternating current, back and forth, 60 times per second. The electric current in the wire produces a circular. Does the current produce an electric field? Yes, because electric charges are present and they produce an electric field. Is it circular? No. Does the current produce a gravitational field? Yes, because charges have mass, and mass produces gravity. Electric charges, moving or not, produce a gravitational field. Is it circular? No. Does it produce a magnetic field? If the charge is at rest, no. If the charge is moving, yes. It produces a magnetic field. What's the shape of that magnetic field? Circular. That's going to be our answer, right? Circular magnetic field around the wire. D, you haven't even learned about an electromagnetic field. We're going to learn about that in our next unit. Okay, but that's not the answer. Otherwise, I wouldn't have given you this question if that was the answer. A DC current doesn't even produce any electromagnetic field. An AC current does, but even that AC current doesn't produce a circular electromagnetic field. It produces a sinusoidal electromagnetic field. Don't worry about that right now. There's a lot of detail coming about that in our next unit.
So just to clarify, the short
Yep.
line and the long line side by side are like your battery.
Yep. Yeah. So technically, to go back to that question again for a sec, yes. Technically, that's actually a cell, not a battery. Technically, although usually when we talk about them as being one and the same. It's not quite true. If you have a 9-volt battery, like one of those little rectangle batteries, that actually consists of 6 little cells. Have you taken chemistry? No? Yeah, I think I asked you that just a couple of days ago. A cell is one little pocket of chemical with 2 electrodes. So that's a cell. And technically, one cell is this, right? If we have a 6-cell battery, which would be a 9-volt battery, then technically the symbol for it would be this. So one cell is this with a negative and a positive terminal. A 6-cell battery would be this with a negative and a positive terminal. But like I say, in physics, because the purpose of what we're doing is not to distinguish between cells and batteries, usually we just call them pretty much one and the same. Okay, you have a 1.5 volt cell, a 1.5 volt battery, whatever. I mean, you buy like a little AA battery. It's not a battery. It's a cell. A battery is a combination of cells. When you put 2 or more of them together, that's actually technically a battery. But we call it a battery. It doesn't really make any difference, right? In chemistry, they might not agree with that. But here, it doesn't make any difference. Okay, does that make sense?